It is my great pleasure to introduce the final speaker and one of the organizers of this symposium, Brown University's T.J. Watson Professor of Science, Leon Cooper. Professor Cooper is world-renowned for developing a microscopic theory of superconductivity with his colleagues John Bardeen and Robert Schrieffer. It was a major breakthrough. They created a model explaining how some materials lose all resistance to flowing electrical currents. Many very famous scientists, including Einstein, had tried and failed over more than 40 years. The importance and impact of their BCS theory was recognized with the Nobel Prize in Physics in 1972. Professor Cooper, in particular, was responsible for conceiving the notion of Cooper pairs of electrons that are at the heart of the BCS theory. Their theory has enabled the development of new technologies and, moreover, very pertinent to today, continues to serve as a cornerstone of theoretical physics. Professor Cooper subsequently made outstanding contributions to neuroscience. In particular, he and co-workers Bienenstock and Monroe proposed a theory for the development of neuron selectivity. This BCM model guided experiments that made long-standing qualitative ideas about learning and memory concrete. He founded and directs the Institute for Brain and Neural Systems, which brings together scientists from across disciplines who are dedicated to understanding learning, memory, and the brain. Throughout his career, Leon Cooper has exhibited a breadth and sensibility that has enabled him to influence developments in many fields of physics, as well as in neuroscience. He has written and lectured on a broad range of topics that span the disciplines including art, history, science, and philosophy. His ability to connect with other intellectual disciplines has earned him the deepest respect of his faculty colleagues at Brown. In 2013, they bestowed on him their highest honor, the Rosenberger Medal. His latest book, Science and the Human Experience, and probably this talk, Can Free Will and Locality Exist Together in the Quantum Theory, will give you a sense of Professor Cooper's broad view on science and life. Professor Cooper.
Is the mic on now? Is it? Okay. Thank you, Jim. Next time we have a meeting, you are my chairman, I'll remind you of what you just said. Today I'm going to treat a subject that is very old. The quantum theory came into existence about 100 years ago. And although it has had incredible successes, what it means, its interpretation, is still an open question. And I am hoping to help resolve that today, and perhaps it will be resolved in the next 250 years. And in particular, we will ask whether free will and locality can exist together in the quantum theory. That's just a come on. What I'm really talking about is the interpretation of the quantum theory. Now, the argument is old. It goes back to Plato and possibly before. Is there a real world out there, according to Plato, or is the real world a construct that exists only in our mind, the solipsistic position of Bishop Berkeley? As Albert Einstein once asked, does the moon exist only when you look at it? And remarkably, this argument resurfaces in a modern context in the interpretation of the quantum theory. Now, the essence of the long continuing debate between Einstein and Bohr over the meaning of the quantum theory does not lie so much in Einstein's seeming rejection of probability, God does not play dice, but in Einstein's insistence that there's a real world and it's science's duty to describe that world. As Pauli wrote to Born, Einstein does not consider determinism to be the key issues. Einstein's point of departure is realistic rather than deterministic. In other words, what Einstein always says is there's a world out there and science's duty is to describe it. But Bohr, on the other hand, continually emphasized the interaction between the observer or the measurement and the quantum world as being crucial. And it has been mentioned in some of the previous talks by Nima and by Frank, this interaction of observer and what is being observed. Now, the argument is complicated by an often made distinction between the observer and what is observed. As John von Neumann stated in his Mathematical Foundations of Quantum Mechanics, we must always divide the world into two parts, the one being the observed system and the other the observer. Possibly one is infinite, possibly one is separated. He says, and this is the incredible thing, we can follow in the former, we can follow all physical processes, in principle at least, arbitrarily precisely. In the latter, this is meaningless. The argument is further confused by the introduction of the idea of measurement as something that disturbs the system and makes the classical variables like p, momentum, and position inaccessible, as though they are there and can't be measured. A revealing interchange occurred in Bohr's country cottage between Klein, Heisenberg, and Bohr. Klein remarks, "Isn't it odd that Einstein should have such great difficulties accepting the role of chance in atomic physics?" Heisenberg says, "We cannot make observations without disturbing the phenomena." Just to keep that in mind. The quantum effects we introduce with our observation automatically introduce a degree of uncertainty into the phenomenon to be observed. This Einstein refuses to accept, although he knows the facts perfectly well. Bohr then responds, "I don't entirely agree with you. In any case, I find all such assertions as observation introduces uncertainty into the phenomenon inaccurate and misleading." I happen to agree with Bohr about that. Nature has taught us that the word phenomenon cannot be applied to atomic processes unless we specify what the experimental arrangement or what the observational instruments are involved. And that's a theme that you have already seen repeated in some of the earlier talks. If a particular setup has been defined and an observation follows, then we can admittedly speak of the phenomenon, but not of its disturbance by observation. Okay, so some of you, of course, will find most of this totally elementary, but I presume that some of you out there don't know this. So I'll talk about the probability interpretation, the distinction between observer and observed, the relation of the theoretical structure to the so-called real world, and measurement, is the quantum theory complete? And then I'll ask, is the quantum theory local? And I'm going to do this in the space of less than 17 hours, so don't get upset. Now, in the quantum theory, for any forces, the Schrödinger equation gives us the wave function of the system. And the equation is the equivalent of Newton's second law, the dynamical F equals ma. And using this, it can in principle be solved for any forces and fields. And it provides the solution for any physical system. Now, its success is beyond belief. It has been the basis of thousands of calculations for molecular atomic systems used to determine the chemical and ultimately the biological processes of these systems. It has been used to calculate the magnetic moment of the electron, which agrees with experiment to 10, not 10 to the 20th decimal places, and other such things as the Lamb shift. It's absolutely amazing. I mean, it can't be accidental. But what does it mean? Now, first I will go through what is called the probability interpretation. Consider an electron moving toward a barrier. The wave function here is, oh, you can see, okay. All right, well, the wave function here, see, accompanying the electron, there's a barrier, which is a little bit of electrons, so they will repel it. And detectors are placed to record whether or not it penetrates. So you have a detector 1 and a detector 2. Now, a classical Newtonian electron would behave, well, classically. A fast electron goes over the barrier. A slow electron rolls back. Fast electron. See, by the way, these are in Keynote. That's why I can get the animations. That's due to P. And the slow electron. So in Newtonian physics, you know exactly. If you know the initial conditions and the forces, you know what's going to happen in the future. But in the quantum theory, the Schrödinger behaves the wave associated with the electron behaves like any other respectable wave at such a boundary. Part of it is reflected and part of it is transmitted. Well, you know, when you teach quantum mechanics, you start by teaching a little bit about wave theory, and you show people that waves and barriers like that are partially reflected and partially transmitted, and then you have springs and so on and so forth, and you demonstrate all of that. So does the electron arrive, I guess it doesn't show over, does the electron arrive at detector 1 or detector 2? This is what the quantum theory tells you. Or perhaps part of it arrives at 1 and the other part at 2. But as far as we know, electrons are indivisible. The essence of the quantum theory is that energy transfers take place in discrete bundles. And the question is, how do we understand this? And the way physicists understand this is through the famous probability interpretation. He says, this is Born, and again, an idea of Einstein's gave me the lead. The Schrödinger psi function, its square, ought to represent the probability density for electrons or other particles. In other words, he interprets the wave function, or its square, as a probability. And so now what you have is that all the quantum theory can tell us about our electron's eventual destination is that it will sometimes register on the right and sometimes register on the left. Now, the reason this doesn't come up as a crucial issue way back in the beginning of the quantum theory is no one ever does this kind of experiment. They do it where it's in effect it's repeated thousands, millions, billions of times. And so what happens is quantum theory tells us in a natural way the right versus the left registrations. But for a single experiment, which can be done, the quantum theory can only tell us the probability of a right or a left registration. And this uncertainty of outcomes is so unpleasant to many. God does not play dice, Einstein's famous thing. And Bohr's response is, stop telling God what to do. That a variety of other possibilities have been explored, and some of these were mentioned before. And some of these are what are called hidden variable theories. Now, in our example, the hidden variable might be, as yet, unseen arrow inside the electron. We haven't seen the variable, it's hidden. Arrow up means transmission, arrow down leads to reflection. Now, such theories actually present very serious technical difficulties. In particular, a famous theorem of John Bell shows that any hidden variable must be non-local. But I think what's more important is that they add absolutely nothing to what's already known. It just encumbers, and I think it's an ideological question. What you're trying to do is to return to a previous determinism for no reason in the world, but due to your ideological preferences. Anyhow, I think now some of you physicists out there might disagree with me, but at the moment it's fair to say that the probability interpretation, with all of its peculiarities and without hidden variables, is the interpretation accepted by almost all physicists. Not all philosophers, but all physicists. Okay, but if we accept the probability interpretation, what do we do with the part of the wave function that shows registry on the non-registered side? Okay, suppose you have registry on the left, or there's a part of the wave function that shows registry on the left and registry on the right. And yet, let's say you see it on the left. What do you do with the part of the wave function that shows registry that didn't happen? This has been a puzzling question ever since the origins. And von Neumann and Bohr would agree with Eugene Wigner in what is called the Copenhagen interpretation. I quote Wigner, "One must conclude that the only known theory of measurement which has a solid foundation is the orthodox one, and this implies the dualistic theory concerning the changes of the state vector. It implies in particular the so-called reduction of the state vector." And what that means is you take the part that shows the registry that didn't happen and you throw it away. And obviously by a process that doesn't follow the Schrödinger equation, you just throw it away. Now, the reduction of the wave function requires that we throw this away. But such wave function reduction is difficult, and I would say impossible to make consistent. But that's the standard one you see in all of the quantum textbooks. And in fact, the way I got into this was Debbie Van Vechten, who was a Brown senior, kept coming to my office and say, Professor Cooper, what about the paradoxes in quantum theory? And I'd say, go away, Debbie, I'm trying to work. There are no paradoxes in quantum theory. And then I began to think about it, and I said, do we really get taught this stuff? And so that resulted in a paper that I will refer to later. Okay, and now the issue arises in terms of what is a measurement and what's the distinction between the observer and what is observed. In some of the previous talks by Nima, by Frank, you see a system, a quantum system, and you see an observational thing, which may be large or small or whatever, but they are separated. And to me, that is one of the problems. It's really very difficult to separate them. And then again, we must always divide the world into two parts. This is the famous von Neumann thing. All right, now I love to quote Spinoza. They appear to conceive man to be situated in nature as a kingdom within a kingdom, for they believe he disturbs rather than follows nature's order. Now, many of these problems can be illustrated by the following somewhat too graphic example. We begin with a single photon approaching a barrier with a double slit. This is the famous double slit experiment. The photon is on the left, and then you have the double slit screen, and then the wave comes through both slits. And then, actually, we can do this. We have an apparatus that does it, and to me, it's the most stunning demonstration. You separate the photons so they're miles apart, and they hit one by one, they hit the screen, and you see them hitting the screen, but after a while, you see an interference pattern. And that, to me, is the dark heart of the quantum theory. Okay, and now we go to the famous Schrödinger's cat that you've all heard of. And this is courtesy of my colleague, Humphrey Maris. All right, we now connect this single photon apparatus to an infernal device in which Schrödinger's long-suffering cat is imprisoned. And the way it works is you have a double-slit barrier, you have an upper and lower detector, you have a cat, and a poison in the box. And if the photon is captured in the lower detector, has to be captured in one or the other, then the cat lives because the poison is permanently locked in place. On the other hand, if it's in the upper detector, then unfortunately the cat dies because the poison is released. And this is a famous thing invented, I think, by Schrödinger and Einstein, but anyhow. But Schrödinger regarded it as totally absurd. But it's not. It's perfectly possible to realize this in the quantum theory. So before we set the machine in motion, we draw shade to spare ourselves the possible anguish of the cat. And now the wave function, you remember the wave function for the single photon looked like that. And remember, it's equal to the upper and lower part, because otherwise you don't get an interference pattern. Now, if you include the cat as well as the spectator, the wave function becomes, and now I'm not really slipping anything over on you, but one of the things I'm going to do is to show that the distinction between the observer and the quantum system is an artificial one that really shouldn't be made. So I put them all into the wave function, and this now will be a superposition of the upper and lower components. In the upper component, there. Okay, now the shade is drawn. The upper component shows a dead cat. The lower component shows a live cat. And this is the famous Schrödinger cat. Now, obviously, if you do this in the real world, what will happen is that you set the apparatus in motion, and the one time you do it, you'll find a live cat, and then you start over again, you find a dead cat, and so on. But you find one or the other, you don't find both, right? All right, now, is the poor cat alive or dead? Well, both. If the cat is dead, when did it die? When the photon registered in the detector, or when the shade was drawn and the observation was made. And you notice some physicists will say that nothing happened until the observation is made, which to me is patently absurd. But anyhow, you realize, I know I'm gagging it up a little bit, but all of these things have been said, and seriously, and defended, especially by philosophers. Part of the problem, and this now is getting to the heart of it, is the connection between the theoretical structure and the world it is trying to describe. And here you have a fundamental difference between the quantum theory and classical theory. In Newtonian theory, for example, if we know the initial conditions and forces, we can calculate the motion. It can be put into correspondence with the world. In the quantum theory, this cannot be done. The wave function, which is completely determined if we know the initial conditions and the forces, it cannot be put into direct correspondence with the world, because the wave function is a superposition of two very different worlds. And the whole idea of wave function reduction is to get rid of the one you don't like. But that's not consistent, so you have to keep both of them. In one, the cat is alive. In the other, the cat is dead. Both are possible worlds, but the wave function, and therefore the quantum theory, cannot tell us which world we are in. It can't tell us which world we will be in the future, and it can't even tell us which world we are in now. You may not like it, but that's the situation in the quantum theory. So, how do we know which world we're in? Why don't we experience two different worlds? These are all questions that have been asked. If the cat died, when did it die? And what does all of this have to do with measurement or observation? First, what do we mean by a measurement? And this is one of the key points that I will be making here. Consider again the single photon arrangement. When can we say that we have measured the position of the photon? Well, you see, I would claim that before the interaction with the screen, the photon has no position. It is only in the interaction with the screen that the photon acquires a position. It's one of these dots. And in fact, what do we mean when we say anything has a position? It's only when we and other observers agree where it is. And for the photon, this occurs when there's an interaction with the screen that for practical purposes is irreversible. And this is one of the key points I want to make. It is these irreversible interactions that give you what we call a measurement. And it gives you what you call the classical world. Without these irreversible interactions, there would be no measurements, no memory, no classical world, nothing. And people have often asked me when I do this, they say, are you going to base everything on accidentally irreversible interactions? Well, the answer is yes. And if they didn't exist, we wouldn't have a classical world. But it's very easy to construct irreversible interactions, the photon interacting with the silver in a screen. Now, it qualifies as a measurement because the interaction is irreversible in the thermodynamic or the statistical sense. Although measurement is often characterized as an observation by an observer thought to be a classical system, or more recently, more fashionably, decoherence due to the interaction with a complex classical environment, this is not necessarily so. It is often so, but it's not necessarily so. From our point of view, what's required is an interaction that for practical purposes is irreversible. And this could be the interaction of the photon with an atom that ionizes the atom and sends the ionized electron to some distant part of the universe. That's irreversible. There's nothing about it that's decoherent. There's nothing about it that's particularly classical, but it will serve. It's an irreversible interaction. It will work. And so it can be regarded as a measurement. Now, if the interaction with the screen were easily reversible, we would not consider it, we wouldn't consider that the photon had a position. Because, I mean, suppose instead of the screen you had a two-level atom. and the photon interacts and goes to the upper level, and then, you know, a microsecond later it drops down and the photon is absorbed. We wouldn't call that a measurement. And you certainly couldn't discard one branch of the wave function, because you need them for the interference. But interactions can be constructed that reverse themselves in seconds, days, years, or the lifetime of the universe. Very easy to do. At what point, then, might it be permissible to reduce the wave function? Our answer is never. You never reduce the wave function. You always keep all of the components. And so the wave function for all time, now as a practical matter, of course you can do it, but the wave function for all time conceptually contains all of the branches. So it may be a linear superposition of two very different worlds. In one the cat is alive and the other is dead. Both are possible worlds, but we are in only one of them. Now how do we know when if the cat died, when did it die? How do we know which world we're in? Why did we experience two different worlds? And do we have to assume the existence of two different actual worlds in what is called Everett's many-world interpretation? Okay, first question. If the cat died, when did it die? In agreement with common sense, the cat died when the poison was released after the photon registered in the upper detector. It is with this irreversible interaction that possible becomes actual in the quantum theory. The irreversible interaction separates the past from the future. It separates the facts of the past from the possibilities of the future. When the observer discovers that the cat is dead, it affects only the state of his own knowledge. He doesn't kill the cat by looking, obviously. It just affects the state of his knowledge. The cat died, and you know, if he left, came back a week later, we could find other evidence of the fact that the cat was alive or dead. So how do we know which world we're in? That's the key question. Quantum theory doesn't tell us, so how do we know? We look. That's the only way we know. We stand there and look, and if the cat is alive, that's the branch we're on. And if it's dead, that's the branch we're on. The quantum theory will never tell us that. We just have to look to find out. It's a limitation of the quantum theory, if you want. Why don't we experience two different worlds? Or to paraphrase Wigner, I am sure of the state of my own mind. How could my mind be a superposition of two such different states? Well, the answer lies in the nature of detectors and minds. The detectors are constructed so that we can have registry in the upper and not the lower, or registry in the lower and not the upper. One or the other, but not both. Otherwise, they wouldn't be proper detectors. And no, the more important is we know the state of our own mind and don't experience two different worlds, because once there's an almost certain correlation between what we observed when we first observed the cat dead and what we will observe in the future, and as well as agreement between all observers once the irreversible interaction has occurred. If you ask us, what is the probability that you will see the other once, you know, it's zero, or very close. So that this gives us the sense of the coherence of our own experience. And, you know, for most of these interactions, that wouldn't reverse themselves in the lifetime of the universe. For practical purposes, you can say you're on one branch or the other. And for practical purposes, you can discard the other branch. But theoretically, it's not necessary, and it doesn't work. And do we have to assume the existence of two different worlds? Some people have interpreted this as saying that you have one world in which the cat is alive and the other world in which the cat is dead, or, you know, 100 different worlds and so on and so on. And the answer is absolutely not. It's a confusion. It has to do with the connection of the theory and the world. We need to only assume the existence of one world, the one we're in. That's what we are trying to describe. The wave function is a linear superposition of two very different worlds. In one, the cat is alive, and the other, it's dead. Both are possible worlds, but the wave function, and therefore the quantum theory, does not tell us which world we are in. The branch of the wave function on which, follow this, on which we are not describes a possible world that did not happen. There were some puzzled faces out there, but anyhow. Okay, so this is, I once gave this to something like this to the American Philosophical Society. And so I quoted Borges. And in contrast to Newton and Schopenhauer, you can read the final thing, the network of times which approached one another forked, broke off, or were unaware of one another for centuries, and it embraces all possibilities of time. And some people knew it and said, wow, art has preceded science once more. And now we go to the question, is the quantum theory complete? You can ask me later questions about that. And is it local? Well, in classical theory, you know, if you know the position at t0 and x0, you can follow it out and you know exactly what the orbit will be. The planets follow almost elliptical orbits. You can calculate all that. A Newtonian particle confined between two worlds would follow a path like that. At all times, we know where it is and how it is moving. For the quantum theory confined between the same two walls, we have only the wave function and its associated probabilities. We cannot tell you exactly what the position is. We can only tell you what the probability of a position is. It does not allow a complete specification of the position and momentum of the quantum particles, because if you try to localize the position, the momentum goes very large. Actually, seems very mysterious, but you know, if you just do a one-dimensional problem of a particle between two walls, and you say, well, if they're this far apart, you don't know the position very well, but you might know the momentum. But if you squeeze it like this, you know the position very well, but the momentum gets very like this. I do this for a high school class. But that's just the intrinsic thing in the quantum theory. So does this mean that something is missing, that the quantum theory, for all of its success, does not give a complete description of the world? Now, to answer such questions, Heisenberg introduced his famous thought experiments. He showed by various concoctions. The trouble with these is that he shows you that one doesn't work, and so then you think, I'll think of another one. And then you think of another one, and nothing works, of course. And so a typical one is like this, is you attempt to determine the position of an electron that has a precise momentum. Now, if you want to determine the position very accurately, you need a very short wavelength of the photons. But the very short wavelength transfers a lot of momentum to the electrons, and so a measurement of position disturbs the momentum, and so you get the idea that the measurement disturbs the system. But what you really want to ask is, does the electron have a position and momentum, and you can't measure them, or does it not have a position and momentum, and so of course you can't measure them? Okay, so what does it mean? All right, now Einstein, Podolsky, and Rosen, EPR, attempted to demonstrate that the electron does have these properties. So since the quantum theory does not, the quantum theory is incomplete. This is their famous, I think it was 1936 or 1937 paper that has been cited very often. Now, I'll give you a variation due to Bohm because it's easier to understand. And you imagine the decay of a pi0 at rest that results in the emission of an electron and positron in opposite direction with total spin equal to 0. And that happens rarely, but it happens occasionally, like that. And so here you have a pi0, and there's the electron and positron going in opposite directions. And the spin part of the wave function can be written like this, and it is gloriously entangled, as some mentioned as an example of an entangled wave function. When the particles are far apart, an observer on the right can measure the spin of the particle on the right. And suppose she measures the spin in the x direction and obtains the value spin up. She then knows that her measurement in the x direction by her partner, who is very far away on the left, will result, or has resulted, since you don't know time, in the value spin down. He must obtain this value since the total spin must be 0. But the observer on the right might just as well have decided to measure the spin of the particle on the right in the y direction, or any direction. Now, if she does that, she cannot move on them. if she does that, she then knows that her faraway partner on the left has or will measure the opposite spin for the left particle. And so it seems as though her measurement here is determining the measurement of another particle light years away, which seems to be very, very non-local. Now, actually, such correlations have actually been observed in an experimentally accessible situation involving two photon atomic transitions by Aspect, Grangier, and Roger. They've been observed. Everybody, all physicists agree that they're there. So EPR conclude either the particles possess X and Y spin in reality, or the way they put it, X and P in reality, or a measurement on the right can influence what happens on the faraway left. As Einstein put it, spooky action at a distance. Now, from our point of view, her choice of measuring the X or Y spin involves an irreversible interaction after which the particle can be said to have either a precise X or Y spin. It is this irreversible interaction any place that determines what universe we are in with all of the correlations that result, correlations that were always there. She's just determining what universe we're in. Now, if the observer is part of the system, part of the wave function, quantum theory tells us the probability of her choice, X or Y spin. Then we are in one branch or the other with all of the resulting correlations that were always there. Is there any non-locality? I'm going to share a secret with you. I think there isn't, but this is something that I resist really thinking about very hard. I just kind of reserve it. I says, you know, someday when I have 3 whiskeys, I'll really get to it and think about it. So I leave it as an exercise for the audience. I think probably you can get away. There's no non-locality. But if she's not part of the system, if she exists as an observer on the outside, then her free choice at some place determines the universe everywhere. And this is surely non-local. So can we conclude that an observer outside the system with free will is inconsistent with locality? I would conclude that. As to whether the other is local, I will leave to you. Such questions are so puzzling that Richard Feynman is let to say, we've always had a great deal of difficulty understanding the worldview that quantum mechanics represents. I cannot find a problem, therefore I suspect there's no problem, but I'm not sure there's no problem. Or maybe Spinoza got it right. Men believe themselves to be free simply because they are conscious of their actions and unconscious of the causes whereby these actions are determined. Now, I say that thousands of papers have been written on this subject, and I haven't read all of them, but the one very important one is Everett's, the relative state formulation of quantum mechanics, and the one we wrote, the one I wrote with Debbie about 10 years later without knowledge of Everett's thing, because it came out in a general relativity thing with Wheeler, and it was pointed out to us by staff. But anyhow, we were unaware of it. And a very nice summary is given by Ingvar Lundgren, The Interpretation of Quantum Mechanics, which is available at that site there. And I'd like to give special thanks to Pete Bilderbach, who not only created the animations, but managed to put it on in Keynote so that you could see them. Thank you very much.